In the previous video, I gave an introduction of epidemiology, its objectives, and its role in the promotion of public health. Now in this video, I will be talking about the basic investigatory tools an epidemiologist uses during disease investigations. Now, when we say epidemiologic methods, we are collectively referring to the different techniques an epidemiologist employs to gather and analyze epidemiologic data. Now, which method in particular depends on the type and extent of the disease an epidemiologist is up against. Nonetheless, all these methods have underlying unifying objectives. The first is to identify the different factors that are causally related to the occurrence of a disease. The next is to assess how much such factors contribute to or increase the risk of occurrence of that disease, once these said factors have been identified. Now, I stressed in the previous video that the terms determinant and factor can be used interchangeably. Now, this factor can either be a risk factor or a protective factor, and I'll be touching on that later in this video. Now, assuming that the association between a factor and the disease is causative, one may expect that the higher the level of the factor, the more frequent the disease occurrence is in the population. Now, consequently, if one manipulates this factor, that is, if the levels or occurrence of that factor is made to diminish or is eliminated from existence, one may also expect that the incidence of the disease is lowered significantly. Well, not necessarily eliminated, since most diseases have multiple factors contributing to their causation. Now, this factor manipulation actually describes the principle behind disease prevention, or the action of stopping a disease from happening or arising. Now, perhaps one way of viewing epidemiologic methods is that these are tools that help you answer the 5 W's in epidemiology, namely the what, who, when, where, and why or how questions often asked in epidemiology. As we will see later, descriptive epidemiology deals with the first 4 W's, while analytic epidemiology deals with the last. So, why should we compile and analyze data using these 5 W's? Well, first is, we want to learn the extent and pattern of the public health problem being investigated. Like, what groups of people in the population seem to be affected more? Is the problem localized in certain neighborhoods, or does it involve the entire province or region? Are there certain hours of the day, days of the week, or months of the year when this problem comes about, particularly if the public health problem is something recurrent or seasonal, and so on and so forth. Next is, we want to create a detailed description of the health of a population that can be easily communicated with tables, graphs, and maps. Now, I'll be talking more about this in the next video. And finally, we want to identify areas or groups within the population that have high rates of or at greater risk for disease. Here, we basically take all the clues we have gathered about the disease, generate hypotheses about these clues, and test them to see if these clues or factors contribute to the causation of disease. So, the first 2 reasons illustrate what is done under descriptive epidemiology, while the last one illustrates what is done under analytic epidemiology. I will be discussing the distinction between the two next. So, epidemiologic methods are generally grouped into 2, descriptive methods and analytic methods. Now, with descriptive methods, the epidemiologist would be able to describe the amount or magnitude and distribution of a disease by knowing how frequent the disease occurs in a population. The epidemiologist would be able to know which type of persons seem to have a higher frequency of the disease, and at the same time describe what particular set of characteristics these persons have, which localities appear to have higher frequency of the disease, and describe what kind of environment these places have, and what timing the disease has, whether it occurs seasonally or sporadically. Now, basically, descriptive epidemiologic methods deal with answering the questions what, who, when, and where. Now, with this information at hand, the next step would then be to ask the question, are these aforementioned characteristics and timing associated in any way with the risk of contracting the disease? You basically start generating hypotheses about possible relationships between these characteristics and occurrence of disease. You then test these hypotheses by making use of analytic epidemiologic methods. Now, with analytic epidemiology, one now ventures into answering the questions how and why. Like, how and why do these characteristics affect disease occurrence? Do they increase or decrease disease frequency? Now, if the epidemiologist finds that these characteristics indeed affect disease occurrence, these characteristics will now be considered determinants of disease. And clearly, a determinant is a risk factor if occurrence of this determinant or characteristic increases the incidence of the disease. But what if the presence of a characteristic decreases disease occurrence? You no longer call it a risk factor, but instead call it a protective factor. So basically, analytic epidemiology tests the hypotheses about the relationships between characteristics and disease occurrence that you have generated under descriptive epidemiology. Now, let's first talk about descriptive epidemiologic methods. Now, these methods make an inquiry into the nature and occurrence of an unknown phenomenon, a very good example of which is the occurrence of cases of unusual or atypical pneumonia in Wuhan, China. Now, descriptive methods also look into how much and how widespread this novel phenomenon is within that particular population, which particular subsets of this population are affected more, and if the occurrence of this unknown phenomenon affects other populations and to what extent. Now, descriptive methods are also interested in the distribution of the phenomenon or disease by person, place, and time, as was described in the previous slide. Are there discernible patterns to the disease, or are they merely random occurrences or variations that occurred by chance? Now, it was also stressed in the previous slide that descriptive epidemiology is the first step in risk factor determination. And that data gathered or generated from this investigation leads to formulation of research hypotheses, like how are these factors related to disease occurrence and severity, and do they increase them or decrease them? So, where do epidemiologists start? Frequently, they start with reviewing routinely collected data, such as from census. If needed, they review clinical records as well as employment health examinations, depending on what the situation dictates. Now, in the case of the pandemic, during the beginnings of the outbreak in Wuhan, investigating teams had to be brought there to collect data and look at the spatial and temporal patterns of disease occurrence. Now, epidemiologists make use of descriptive research to make all their inquiries about the disease and gather all the data that they need about the disease in order to establish risk factors as a step towards understanding cause and effect relationships. Now, I'll be pointing this out again under the disease causation video series. Now, here are the different types of descriptive research, and I urge you to go back to your Medical Research 1 notes to review them so that you don't get lost in the discussion. Now, recall that case reports, case series, and ecological studies provide the weakest evidence for causality. Now, just to define what an ecological study is, it is an observational study that looks into associations between risk-modifying factors on health and occurrence of disease in whole populations defined either geographically or temporally. So, these studies are basically done at the population level, not at the individual level. Now, each participant, quote unquote, is a population or region or country, for example. So basically, ecological studies treat a population as a homogeneous whole. Now, the danger with this is people would incorrectly extrapolate results of ecological studies, which are based on aggregate regional or national data, onto individuals. This is called ecological fallacy, which is basically flawed reasoning that arises when inferences are made about an individual based on aggregate data from a very large group. Now, the problem with ecological studies is that aggregation of data at, say, a national level invariably results in the loss or concealment of certain details of information. Thus, it is completely wrong to apply conclusions of ecological studies on individuals. Now, why perform ecological studies then? Well, they're always a good place to start, particularly when investigating phenomena or disease occurrences that affect people at a large scale. If associations are detected, then this prompts epidemiologists to make additional hypotheses to dig deeper into the issue. Likewise, ecological studies are often used to measure prevalence and incidence of disease, particularly when the disease is rare. Now, cross-sectional studies provide stronger quality of evidence compared to the first three in the list. However, because data is collected at only one point in time sequencing between a designated cause and a designated effect can only be inferred. We call this limitation temporal ambiguity. Now, please review your Medical Research 1 notes regarding this. So basically, compared to most analytical studies, the ability of cross-sectional studies to prove causation is still weak nonetheless. Notice as well that I place an asterisk here. This is because cross-sectional studies can be both descriptive and analytic in nature, depending on the research objectives. Now, here's an example of an ecological study. Here, the researchers made use of overall meat consumption data in grams per capita for each country included. The corresponding colon cancer incidences per 100,000 women for each country was also used, and this scatter plot was generated. Now take note that each participant, in quotation marks, or more accurately, each unit of observation is not an individual person, but rather the entire population or group, and what the points here indicate are the averages for each population or country. Now, from this scatter plot, we can see that countries with the lowest meat consumption appear to have the lowest rates of colon cancer, and the colon cancer rate among these countries progressively increases as meat consumption increases. However, we have to be careful with its interpretation. Keep in mind that people's meat consumption will probably vary a lot within each country. Meat consumption, which is the exposure assumed to be causal of colon cancer, is measured as averages, and it also assumes that everyone in each population consumes meat. As I discussed in the previous slide, ecological studies are a good start for exploring relationships between putative exposures and outcomes. Now, in this case, additional hypotheses can be generated about meat consumption and colon cancer incidence, and future studies at the individual level can be designed to see if there is indeed a dose-response relationship between the two, for example. Now, here's another example of an ecological study, very similar to the previous one. Now, this time around, the relationship between milk consumption and incidence of ovarian cancer per 100,000 women was investigated at the population level. Note again that each point in the scatter plot represents a country, and the average milk consumption and average incidence of ovarian cancer for each country were used to graph these points in the figure. Now, in this graph, we see that there's a strongly positive relationship between the amount of milk consumption and the incidence of ovarian cancer. However, the same caveats that were discussed in the previous example very much applies in this case as well. And mind you, relationships are not always linear in nature, like with the two examples I just gave. Now, this third example here is from the New England Journal of Medicine, and is a more humoristic, tongue-in-cheek study that showcased the linear correlation or relationship between the annual per capita chocolate consumption per country and the number of Nobel laureates per 10 million population. Now, of course, this is in no way implying that the more chocolate you consume, the higher the chances that you become a Nobel laureate. Now, if anything, the higher risk of getting diabetes is what you will get from doing so, especially if it's commercial milk chocolate that you consume. Now, what this really reflects is that higher chocolate consumption can be indicative of a stronger economy, and therefore higher budget allocation for research and other academic pursuits, which then increases the chances of developing or discovering breakthroughs, which can propel researchers into the list of Nobel Prize candidates. Now, I will wrap things up for descriptive epidemiology by summarizing its uses. Descriptive epidemiology is important for disease trends. Also, if one is familiar with the burden of disease in their localities or territories, policymakers can make use of the data, assuming they're not corrupt, to come up with plans that would efficiently allocate limited resources, as well as educate populations within those territories to prevent or mitigate the spread of the disease involved. And lastly, something that I have mentioned a few times in the previous slides, descriptive studies are important in generating hypotheses that look into relationships between possible exposures and disease occurrence. Now, once these hypotheses are generated, we then go on and test this hypothesis using analytic methods, which will be discussed next. Now, with analytic methods, we start off with a determinant or set of determinants that were identified in descriptive studies and are hypothesized to be causative of or put someone at risk for a disease. So, the main research question now in analytic epidemiology is, does an association or relationship exist between an exposure believed to be the cause of the disease and the occurrence of the disease in question? Now take note as well that the term exposure is interchangeable with predictor variable and independent variable, while the term disease can be interchanged with outcome variable and dependent variable. Now, the critical distinction analytic methods have from descriptive ones is that analytic methods involve studies designed to test hypotheses generated by descriptive methods, and that one I have stressed quite enough during the past few slides. So with analytic methods, we are no longer describing the disease in terms of averages, counts, frequencies, or percentages. Now, with analytic epidemiology, we analyze these averages, counts, frequencies, and percentages to see if a suspected exposure is indeed associated with or causative of the disease of concern. And the absolute requirement here is that you have to have a comparison group. For the exposure status, there has to be a comparison between exposed and unexposed, and we want to see if the occurrence of disease is different between these two groups. Now, try recalling randomized controlled trials where we want to test the hypothesis that the medication can treat the disease effectively. The two comparison groups in this case will be the group that gets a medication and a group that does not get the medication. Then you follow them to see if the cure rates of the disease are different between the two groups. Now, you'll notice with my discussion that I have been regarding both exposure and disease status as something dichotomous or having only two possible values. That is, either you were exposed or unexposed, and depending on your exposure status, either you have acquired the disease or not. Now, in order to facilitate analysis of this data, we make use of a 2x2 contingency table, which looks like this. Now, you can see that the rows represent the exposure status, that is, whether the individual was exposed to the factor or not, while the columns represent the disease status, that is, whether the individual developed the disease or not, given the exposure or lack thereof. Now, in this particular 2x2 contingency table, we have 4 cells, each representing a particular group of individuals given their exposure status and disease status. A. Exposed individuals who develop disease. B. Exposed individuals who remain disease-free. C. Unexposed individuals who develop disease. And D. Unexposed individuals who did not develop the disease. Now, by analyzing the counts contained in each cell, we then determine if there is indeed a relationship or an association between exposure and disease, and make use of the chi-square test for that. Now, the issue with chi-square is that it only tells you if an association exists or not. You will need, however, to compute for the odds ratio to be able to quantify the strength of the relationship, to see if this relationship is statistically significant or not. That is, however, beyond the scope of this video lectures, but you will be revisiting them in Medical Research 2 in the second semester. Now, similarly, you may have already covered this to a certain extent under Medical Research 1. Now, the descriptive methods that I've been discussing from earlier on are all observational in nature. Analytic methods, however, can either be observational or experimental. Now, with observational methods, the researcher or investigator merely observes the exposure and disease status of each study participant. Now, as the term implies, the researcher is neither administering an intervention nor is he manipulating the level of exposure on the participants. Now, here are the general types of observational analytic methods. Now, I'll leave it to you to review your Medical Research 1 notes on the basic research designs. Now, take note as well that the cross-sectional study design is also included in this group. Now, with experimental methods, on the other hand, investigators or researchers manipulate the level of exposure or intervention for each individual or community. Now, the effects of the different exposure levels or dosages on disease occurrence are then tracked over time, implying that research designs under this group are prospective in nature. In medical research, outcomes are not limited to disease occurrence. Outcomes such as cure rates, disease-free survival, time to disability, relapse rates, death rates, and so on and so forth can also be measured depending on the research objectives. Now, clinical trials and community trials are study designs included under this group. The hallmark of experimental research is randomly assigning participants to different treatments, as you have learned under Medical Research 1. Now, with clinical trials or randomized controlled trials, individuals get randomized to treatment groups, as opposed to community trials wherein whole communities get randomly assigned to treatment groups.